Our third speaker for the session is Jan-Niklas Boyn from the University of Chicago. So Nick is one of my graduate students in my research group, and he's going to present some of our recent work looking at applying the variational 2RDM theory to some interesting problems in transition metal chemistry and basically inorganic chemistry as well. So a little bit of an introduction to some of the theory and then also discussion of some of this recent work. So Nick, whenever you're ready to get started.
All right, thank you. Screen here. Let's see. All right. Can everybody see this?
Looks good. Yep.
Mentioned today, I'm going to give a little overview of our recent kind of applications of the variational 2RDM method in collaborations with experimental groups at the University of Chicago. So this is a little bit more of a chemical talk for those so inclined. I will still give a little brief overview of the V2RDM background, and Eugene already gave an excellent overview of this as well. So as was previously mentioned, due to the fact that fermions and electrons interact pairwise, we can express the ground state energy of any many electron system as a linear functional of the 2 electron reduced density matrix, and we can, as such, minimize the ground state energy variationally as a function of the 2RDM. However, variational minimization really requires us to impose n-representability constraints that assure that our 2RDM actually represents a physical n-electron system. This was first really implemented for chemical systems in the early 2000s. However, modern V2RDM algorithms really apply variational 2RDM in a CAS-SCF scheme by computing the 2RDM without the wave function. And this goes back to like 2008. And in this case, we get computational efficiency that leads to polynomial scaling rather than the exponential scaling of typical CAS-SCF. The algorithms that underlie these modern variational 2RDM implementations are such so-called boundary point semi-definite programming algorithms that really, as Eugene mentioned earlier, with the D, Q, and G conditions, allow us to get polynomial R to the 6 scaling, where R is the number of basis functions. And as many people are familiar with, CAS-SCF often presents really the bottleneck of modern electronic structure simulations, as we get exponential scaling and we're really limited to like a 1616 on common computers, maybe 2020 on a supercomputer active spaces. As I just mentioned, the accuracy of a variational 2RDM calculation really strongly depends on our adherence to the n-representability constraints. These really go back to the 50s and 60s, where these were first enumerated. And in particular, the 2RDM needs to be Hermitian, normalized, permutationally, needs to retain permutational symmetry, and it needs to remain positive semi-definite. However, more complete p-positivity constraints were also later implemented in the 2000s. And this is basically a hierarchy of higher order p-positivity constraints that may just be derived by the overlap matrices, where C are just the combinations of creation and annihilation operators. The most commonly used set in our calculations are really the 2 positivity constraints, which are just the 2D, the 2Q, and the 2G conditions. These conditions really physically restrict the probability distributions for 2 particles in the 2D case, 2 holes in the 2Q case, and 1 particle and 1 hole in the 2G case to be non-negative with respect to all unitary transformations of the 1 particle basis. Then higher order 3 positivity constraints have also been enumerated and been actually applied. However, as has been previously mentioned, these scale much less effectively. However, we can form these 2 less strong subsets of the 3 positivity constraints called the T1 and the T2 constraints, which are just additions of two of these constraints. And the advantage of using these is that these can be enumerated just as simple functionals of the 2RDM only, and these don't actually contain any 3RDM terms. And these are also commonly implemented in our program. All right, with that little bit of background, I'm going to move on to our applications of our variational 2RDM algorithms. In particular, We've been working very, very closely with Professor John S. Anderson's group at the University of Chicago. This is an inorganic chemistry experimental group, and they're basically on the hunt for transition metal compounds with interesting electronic structures and interesting electronic properties that are really targets for applications in the development of single molecular magnets, spintronics, molecular switches, qubits and wires, and so on. And in general, they have been focusing on kind of these scaffolds that are transition metals linked by tetrathiofulvine tetrathylate, or TTFTT. It's a real mouthful. Kind of this linker, this linker here, or kind of quinoid bridged linkers. And in general, these are very high spin, highly open shell systems, and they're not well described by single reference methods such as density functional theory and as we have multiple metal centers, they require fairly large active spaces for accurate treatment. So I'd like to talk about this, this first complex we have been doing some work on, which is this cobalt quinoid dimer, which was shown on the previous slide. It's just two cobalt centers that are kept by these bipyridine ligands, and then they're linked by this quinoid bridge. So this has been experimentally synthesized and characterized, and they've done SQUID, so superconducting quantum interference device metronopy, which basically measures the temperature-dependent magnetic susceptibility. And you can really fit this to the Van Vleck equation and get a value for the exchange coupling and as such the spin state splitting of these compounds. And basically what we see is that we have a very, very small exchange coupling, J coupling term of -2 wave numbers, meaning we have a low spin ground state with a very, very low lying higher spin state. In general, in the kind of inorganic and experimental chemistry community, this is commonly rationalized by a super exchange mechanism. So you would, by chemical intuition, expect this compound to have a low spin ground state. And you would expect this basically to happen because you have these, basically, let's imagine we have two unpaired electrons of these cobalts, and you have basically a paired density on this bridging ligand. You basically imagine that these electrons on the cobalts will interact with the pair on the ligand, and you will get basically anti-parallel alignment of all these spins. DFT calculations fail to yield a coherent structure, and they basically do many different functionals yielded different spin state splittings, and broken symmetry DFT also didn't yield any coherent results. So we took out two V2 RDM and basically ran 1414 ACT-CAS calculations on this. We also ran larger CAS active space calculations on this. However, 1414 yielded converged results. So we stayed with that. And basically what we discover is that we get a symmetry broken triplet ground state with two cobalt centers of different net spin. So one which has a net spin of about 3/2 and one which has a net spin of 1/2. All of these are strongly correlated. As we can see, we have really 6 orbitals in the active space that are strongly correlated. And in none of these orbitals and none of the orbitals on the active space, we have actually any electron density on the quinoid bridge. Now we ran the entire spin manifold. And what we basically get is that we have a triplet ground state with a very, very low lying quintet state at 7.77 wave numbers. And we have high energy singlet and septate stage, which are inaccessible. So this compound is not actually a singlet ground state. And indeed, if we now assume that the triplet quintet get roughly corresponds to 4J, so 4 times the exchange coupling constant, that gives us a J of -1.9 for wave numbers, which is a really, really excellent agreement with the experimentally measured value of 2 wave numbers. And this is just using the D, Q, and G condition in this case. Now, the fact that we can accurately reproduce this exchange coupling and spin state splitting, however, we don't see any electron density on the bridge, really suggests that the bridging ligand may not be actually involved in any kind of exchange mechanism. So to further investigate this, we just removed the quinoid ligand and capped these 2 cobalt centers with hydrogens in their fixed positions. No reoptimization, so they're just fixed. So the cobalt-cobalt distance remains identical. Now running this again, we actually get identical orbital picture. I just showing the top to the HONO and LUNO here already, but we get an identical orbital picture to the capped version, and the linker really doesn't have any involvement in these active space orbitals. And again, we get a triplet ground state, we get a quintet excited state, or not excited state, quintet spin state that is accessible at 196 wave numbers, and the singlet remains inaccessible. So indeed now, removal of the bridge actually leads to our J value to increase by about a factor of 20. So we get a J value of -49 wave numbers instead of 2. This really suggests that the linker really isn't involved in any kind of super exchange pathway, but rather even plays a shielding role. And overall, we actually have this exchange coupling that happens by entanglement rather than super exchange, which does not take place. Lastly, another thing we then investigated is, can we actually get the linker involved in any kind of exchange interaction? And it has been experimentally known that these quinoa linkers can be radicalized. So through vertical ionization, we just remove an electron. So we have a radical linker. And it has been experimentally known that these lead to very, very large exchange values compared to the closed shell systems. And indeed, this substantially changes the overall picture. We basically have unpaired electron density delocalized across both the Cobalt centers and the radical linker. And we see a significant increase in our spin state splittings. So we have a doublet ground state, an accessible quartet at 13 wave numbers, and an accessible sextet at about 220 wave numbers. So indeed, in agreement, variational 2 RDM also predicts that in agreement with the experiment, we see larger spin state splittings and exchange coupling interactions for radical ligands. All right, now next I would like to move on to this iron TTFTT dimer. This is a very interesting system that's been synthesized by Anderson's group as well. And they basically synthesized this, ran some spectroscopy on this, and were just baffled by what they saw. So basically looking at the magnetic susceptibility, they got this kind of S-shaped curve, which really kind of suggests that there's some sort of spin crossover happening in the 150 to 200 Kelvin range. And even more interestingly, they did most biospectroscopy on the low spin and high spin states. And they basically see that in the high spin state, you have a high spin iron 2, so each iron with 4 unpaired electrons. While in the low spin, you have low spin iron, so no unpaired electrons on the irons. However, at 0 Kelvin, the magnetic susceptibility does not actually go to 0, so you still have unpaired electron density. So where is this electron density? So they took crystals to extract crystal structures at room temperature and 100 Kelvin, and we actually see that there's significant structural differences. So the central CC bond has different lengths, and the coordination environment around the iron is slightly different. So we basically took the low temperature crystal structure and then ran pretty large 1820 active space variational 2 RDM calculations on these. And what we see is that we actually have a open shell singlet ground state with a very, very low lying near degenerate triplet state. And most interestingly, all of this unpaired electron density is just completely localized on this bridging ligand. None of this electron density is localized on the iron centers. So at low temperature, we really have a completely organic biradical. These are very, very rare and of really high research interest as they are candidates for qubit and molecular information storage development. So what really happens in this compound, we then ran some simple DFT calculations on just the high spin states to see what happens. And indeed, in the low temperature, even in the triplet, DFT also predicts the spin density to be on the linker. And then as you go to the high spin state, the high temperature state, you basically see a transfer of all this electron density to high spin iron. And this is a reversible process. So what happens is we have this iron dimer that we can cool down and heat up. And basically we transfer all the unpaired spin density from these iron centers onto this organic ligand. The Jan-Niklas groups then carried out some more experiments, and they actually did indeed validate by EPR and variable temperature electronic spectra that at low temperature, you do actually have the signature of an organic biradical. So currently, further research is being undertaken on these by changing the ligands and changing the metal centers in order to basically synthesize a molecular qubit using these kind of scaffolds. Lastly, I want to just quickly talk about a very, very similar chemical system, which is this stacked nickel dimers. It's essentially the same scaffold, just that in case of bipyridine ligands, you have these phosphine ligands in the end, and instead of 2+, you have 1+. So you have a single radical TTFTT bridge. These are well known, and that's nothing super exciting. So it is known that the radical will reside on this. It's just the biradical that was unknown. But the interesting part about this compound is that in both solution and the solid state, it kind of forms these interesting dimers and trimers. So it doesn't just float around by itself, it stacks. So, I mean, it forms kind of radical pairs. You would kind of expect that, I guess, but it is fairly uncommon. In particular, this forms these parallel dimers, orthogonal dimers, and orthogonal trimers in both solution and the solid state. So they asked us to run some calculations on these and see what kind of interaction drives these stacking properties. So we ran variational 2RDM with 1820 and 1720 in the case of the trimer, as we have doublet ground state on these different geometries from the crystal structure. And basically what you see is that you have these radicals coming together and stacking and interacting with each other. And you basically, the more overlap there is between the orbitals, as is expected from chemical addition, the more of a bonding and anti-bonding interaction you get. So just looking at the parallel dimer, right, we have a decent amount of overlap. We get a HONO with 1.5 as the natural occupation number, and a LUNO with a 0.5 of the natural occupation numbers. So they still retain a decent amount of strong correlation and biradical character. Obviously, as you twist these and you have the orthogonal dimer, you get more strong correlation, more biradical character, and less of a bonding and less of an anti-bonding interaction. And then as you move to the trimer, it just splits into the typical bonding, non-bonding, anti-bonding kind of set of orbitals. But interestingly, in all these cases, significant unpaired electron density remains. And looking at these orbitals, we can see that the unpaired electron density really is delocalized across the stacks. So this really makes this a viable candidate for the development of kind of molecular wires, 1D and 2D conducting materials, and further research is currently being undertaken in synthesizing these as like a polymeric or 1D and 2D kind of scaffolding material. And the further work on this is currently being undertaken. So with that, I would like to thank you all for listening. I'd like to really thank the entire Mazziotti group. At this point, this picture is, I think, a couple years old. This is pre-pandemic, so things have changed a little bit. And I'd like to especially thank Professor David Mazziotti for all his guidance and insight in the last few years, and Professor John Anderson for really coming to us with all these interesting compounds and experimental measurements and asking us to do these calculations on them and giving us the chance to really showcase our methods. And then I'd like to thank Giazi Z and Heidi Kawamura, who were the John's grad students that really carried out all of the experimental research. And with that, I'd like to ask if there are any questions.
All right, let's first actually thank Nick for an excellent talk here. So everybody, let's unmute for a moment, a little bit of applause here. Great. All right, cool. We have some time for some questions. So please raise your hand if you have a question, or you can basically put a question in the chat as well. All right, don't be shy if anybody. Oh, Sabri?
Yeah, I can start that. I mean, I found the entanglement versus the super exchange really very, very exciting phenomenon. I mean, first of all, do you know the lifetime of this, how far this entanglement can survive?
We actually don't know that lifetime. I don't think, and they have measured this. They're working on similar compounds right now where they are actually, they're working as like a kind of molecular qubit. So they are working on compounds that they're trying to use, trying to turn into molecular qubits where you need a long lifetime. But I think the problem with this one is that the exchange coupling value was so small that in general, they were looking for ones that have a larger value of J, which is necessary for a longer lifetime as well. So I don't think this one was an ideal candidate, but they're currently looking at different kind of metal scaffolds that have a larger coupling constant and larger lifetime.
Yeah, the other point, like if you have entanglement, if I do local interaction or local measurement in one side, I should affect the outcome of the other side. Do you know if experimentally can they do anything locally on one side and see the effect on the other side?
I honestly don't know, but I kind of don't think so, just because I don't know, because they have them in solution or in like a crystal, so you just have like, I guess, like in large numbers of them in random arrangements. So I'm not sure whether that would be possible. I'd have to ask the experimentalists about that.
Thank you.
Yeah, Nick, just to follow up, so maybe I guess if one could break the symmetry on the molecule somehow, you know, like you'd have to have a difference between the two sides, perhaps. I don't know.
Yeah. Yeah. Well, we have the symmetry breaking, but you know, on average, you know, in the whole thing, we
Yeah,
won't
but I
see
mean
any
something more
symmetry.
detectable. Yeah,
Yeah.
something you could actually
Yeah.
detect or something.
Yeah.
All right. All right, cool. All right, let's thank Nick again for an excellent talk. So great. All right. All right, so pretty much that concludes our first session. I want to remind everyone that we have the flash session coming up